Hello everyone, and welcome to this webinar by Mura Technology on chemical recycling of waste plastics using catalytic hydrothermal reaction, or CatHTR. My name is Jeff Brighty and I'm an advisor to Mura, and it's my pleasure to introduce to you Richard Daly, Managing Director of Renew ELP, and he is leading the first commercial scale build of a catalytic hydrothermal plant in the UK at a place called Wilton in the northeast. Hi Richard,
Jeff.
how are you doing?
Hi Jeff, thank you.
If you're able to just share your screen and then we can go through the presentation, thank you.
No problem. Okay, so hopefully my screen is now sharing.
It is, it's perfectly clear, thank you.
Excellent. So today I'd like to run you through our advanced recycling technology, the CatHTR process, and how we aim to convert waste plastic to valuable chemicals and oils. So really, I suppose the first thing to sort of highlight is why are we doing this? I suppose everybody is now fully aware of the global plastics pollution issue, and some of the statistics on this slide do make quite frightening reading. So we can see we make around 350 million tonnes of plastics per year, of which only approximately 14% is collected for recycling. And it's expected that by 2040, production will almost double to around 600 million tonnes. So we can see that currently around 8 million tonnes of plastic enters the world's oceans annually, and this is only set to increase unless we can do something about it. So we are at the forefront of a new technology drive to find solutions for this problem, waste plastic pollution, and that's what we'll go through today. So the CatHTR process is a hydrothermal liquefaction process which falls under the banner of chemical or advanced recycling. So this encompasses many technologies. However, there is no defined governmental regulation for what chemical recycling is. There are various definitions, and one which fits quite well is that proposed by Chemical Recycling Europe, which states that chemical recycling is defined as any reprocessing technology that directly affects the formulation of the polymeric waste or the polymer itself, and then converts this into a substance or product, whether for the original or other purpose, however excluding energy recovery. And what that means is that we take in the polymeric waste and we convert that for a second use. However, this is not to be used as a fuel. So conversion to fuel is termed recovery. There are a number of technologies that look at this. Some of these technologies are focused on individual polymer types. Others are looking at general mixed waste, but all produce products for use as chemicals, potentially, ideally, as a replacement to make virgin plastics. So technologies cover such processes as depolymerization, pyrolysis, gasification, and then hydrothermal liquefaction, which is the CatHTR process, which I'll go into in a little more detail, and also others which are solvent-based dissolution type processes. So as mentioned, some are aimed at specific polymers, such as PET, and others, such as pyrolysis or hydrothermal liquefaction, are taking general mixed waste to make new materials. So this is often sometimes referred to as feedstock recycling also. So here is a very simplified overview of the CatHTR process. Effectively, we are taking in waste plastics, and the first step is then to take this plastic material and remove as much of the non-plastic component as possible. So we effectively clean the waste plastics, take out non-plastics such as glass, grit, other contaminants such as paper, and we then shred these down to be fed into our process. We then melt and pressurize the plastics and mix it with supercritical steam. We then add heat to get to our reaction conditions, pass these through the CatHTR reactors, and we then depressurize at the end of this process into our liquid products, which we then store for onward sale. So in summary, it's a continuous process which takes approximately 25 to 30 minutes, and it's quite simple really. So the key to our process, or what makes us different from other technologies of this nature, is the fact that we're a water-based process, and we're using supercritical water or supercritical steam. And what that means is under this supercritical state, there is no separate phases of liquid and gas. It is effectively a unary system, but it exhibits both properties of liquids and gases. And that means that the supercritical steam or water can actually pass through solids like a gas, but it can also dissolve things like a liquid. and it's the properties of the supercritical steam that we take advantage of in our conversion process. So we're actually using the steam as an organic solvent. And what happens is, as we break the hydrocarbons down into shorter chains, the hydrogen from the steam or water is actually donated to our reaction products. The steam itself has been used to heat the plastics, and as we're a water-based process, we can actually control our temperatures. Although heating quite rapidly, we can control temperatures to avoid excessive temperatures that may contribute to excessive cracking or char formation. And because of this direct contact heat transfer between the steam and the plastics, this means our process is uniquely scalable. This means that we can look to build these plants at large scale, which is what the industry is really looking for. So taking advantage of this water in this way allows us to have a very thermally efficient process and also to have high conversion yields. So typically, on a dry ash-free basis of the plastic fed in, we see around or up to 85% of our liquids of our plastics being converted to liquid products. So this is what's available to make new plastics, chemicals, and new materials. Oh, excuse me. So this is a representation of the first commercial scale plant that we're looking to build on the old ICI Wilton site in Teesside in the northeast of England. And this represents we're building this in 20,000 tonne per year modules. So we look to have 4 of these processing lines on the site when complete, giving us a total processing capacity of 80,000 tonnes, but this representation is a 20,000 tonne plant. So as you can see, as we went through in the basic process flow diagram, we have the plastics cleaning section, and we then have the storage and feeding process into the main core technology. So on the diagram shown here, the core technology really is the gold structure. So within there houses the reactors, the distillation column, so that's the heart of the technology. So downstream of our reactors, you then have the product storage tanks where the products are stored for onward sales. So from a feedstock viewpoint, our target material is the plastic streams that are left over after mechanical recycling. So we can take in any polymer types of 1 through 7. However, we would look to limit PVC if possible because of the risk of contamination of our product arms with chlorides. But we can take in all polymer types. So this includes both films and rigid plastics from various sources. So we could take an agricultural waste, anaerobic digestion waste, or the waste that's left over after the material recovery facilities or mechanical recycling. So we don't need to separate the polymers. We can take in mixed plastics and mixtures of both films and rigids, and we can also handle organic contaminants such as food waste, paper, plastics. And because we're a water-based process, there is no need to pre-dry the feedstock. This means we're also able to process complex, multi-layered, flexible packaging, which is a known problem for current mechanical recycling. So in summary, our feedstock is what's left after mechanical recycling and what is currently used as a fuel for incineration or energy from waste, or is effectively used as landfill. So from taking in this mixed waste plastic, we produce a range of hydrocarbon products. So the process itself, as we let the pressure down at the back end of our reactors, effectively the majority of the liquids flash off as a vapour, and we pass this through a distillation column and then separate out the liquids on a boiling range into the product lists on the slide. So we produce a lighter end, which is a naphtha, which is ideally suited as a steam cracker feedstock to make new virgin plastics, and a distillate gas oil fraction, which is also suitable as a steam cracker feedstock. So the ideal use for this is also to make new virgin plastic material, but also it could be used to make other chemicals such as solvents. The heavy gas oil fraction tends to be a little bit on the heavy side for a steam cracker feedstock. However, it is an ideal feedstock for other refineries that are looking at making base oils, waxes, and other chemical products. And then we're left with a high boiling, heavy wax residue fraction. And this is the fraction that contains a lot of the solids that come in with the plastic stream. So this is the ash and the fillers that are in with the solids. And really the ideal use for this is as an additive in the bitumen or asphalt industry. So because of the solids content, this is really the ideal use for this fraction. So all of our products are currently going through a REACH registration process to allow us to export these into the EU, so they'll be classified as chemicals. So using our CatHTR process does have some significant advantages, one of which I've touched on being the fact that we're directly contacting the steam and the plastics flow, and this gives us a very efficient and controllable process. And because some of the properties that I touched on earlier of how the steam interacts and breaks the plastics down, this actually allows us to get very high liquid yields from our process. So because this is a water-based process, we can actually control the reaction conditions and influence the cracking rate, or the rate at which we break these plastics down. And importantly, that then allows us to bias our product split towards either the lighter end, the sort of naphtha end of the range, or the more heavy, the waxier end product. So we can tailor our products towards the fraction that the market most demands. And I previously touched on another advantage of the process being that the hydrogen from the steam or water itself is actually donated to our products, which significantly reduces complexity and cost for us. Also pleased to mention that we were recognised by the UK government and were awarded a grant from Innovate UK to aid towards commercialisation of the first facility in the UK. And this was done under the industrial strategy, the Smart Sustainable Plastic Packaging Programme, which was really aimed to find new technologies, providing innovative technical solutions to problem plastic packaging. So it recognises the commercial scale, feasibility and potential impact of our technology for this global issue. So from an environmental perspective, because we can process waste plastics that current traditional mechanical recycling cannot, this means that we're increasing the scope of plastics recycling. So this is diverting material away from recovery operations such as landfill and incineration. We're effectively moving this waste plastic up the waste hierarchy from recovery to recycling. So our products are sustainable because there's no limit on the number of times that our process can recycle these. So we can take in waste plastics, recycle them back to oils, which can be used to make new plastics. And once these plastics have been used, this waste plastic can come back to us. And there's no limit on the number of times that this process can happen. This means we're helping contribute to a truly circular economy and also reducing the dependency on fossil feedstocks. So from a CO2 emissions or a GHG emissions viewpoint, there have been a lot of studies done on chemical recycling, the advantages from an environmental perspective in this nature. And some independent studies that are run by the University of Delft for the Dutch government to look at chemical recycling as a whole have concluded that compared to incineration, that chemical recycling per tonne of input would actually reduce CO2 emissions by 1.5 tonnes. This means it's a significant environmental benefit from moving this material away from incineration and into chemical recycling. So for a 20,000 tonne processing line, this would be a saving of 300,000 tonnes of CO2 emissions per year, which is a significant benefit. So from a technology development or a global rollout perspective, my focus at the minute is on the first commercial site in the UK. However, in the pipeline, we are looking at development opportunities with target markets such as North America, Europe and Asia. And these sites that we're looking at, facilities, we're looking to build up to the sort of 200,000 tonne per year processing, which is a significant volume. So by 2025, we're looking to have around 500,000 tonnes of global capacity under development, all of which will follow the first commercial scale plant that we're building here in the northeast of England, which will ultimately process 80,000 tonnes on completion. So from an Asian perspective, we're already looking at opportunities in this market, such as Malaysia, Korea, Japan, China and India. And these are all countries that have a waste plastic problem, and regulations are aiming to help tackle this issue. The waste plastic problem and pollution continues to grow in the short term. So each of these markets offers a level of waste collection infrastructure and access to this waste, allowing us to develop these opportunities at large scale. We would like to take this opportunity to invite the local partners to contact us and assess the potential of developing partnerships to help develop our technology in Asian markets.
Thank you very much, Richard, for taking us through the process of catalytic hydrothermal reaction. Got a couple of questions, if I may, just to elaborate a little bit further. You've just finished on the commercial aspects of the technology and obviously the ambition of Mura to take this to wider markets. So what do you see as some of the biggest barriers or challenges facing the commercial success of the CatHTR process?
I think it's not just the CatHTR process, Jeff. I think it's the chemical recycling industry as a whole. This is an industry in its infancy, and it's a new and disruptive technology industry, and we are fast or rapidly outpacing regulations and legislation. So we really need these regulations to catch up, recognise the impact that chemical recycling can play in various waste strategies in dealing with this issue, and also to implement policies that support the growth of this industry. So clarity on regulations about recycling and contributing to recycling credits, and actually introducing regulations and legislations that support the growth of this industry and to promote the chemical recycling as a recycling route for this waste plastic material.
Thank you. And in terms of the feedstock, you mentioned about mixed plastic waste coming into the plant. So what are the sources of the plastic feedstock that you're particularly looking at?
So for the initial plant here in the UK, what we're looking at doing is focusing on post-consumer household waste. So this is waste that's collected from households and then passed through mechanical recycling facilities. And then what we're interested in is the plastic fraction that's left over after this process. So this is what's left over that mechanical recycling can't actually process or recycle. And as mentioned, would typically end up as a fuel for energy from waste, incineration or landfill. So our target is post-consumer household waste. We may look at other sources such as industrial waste or waste electrical equipment, but for the first plant, we're focused on post-consumer household.
And you've talked about the products that come out of the CatHTR process runs. Those products, are they able, in effect, to replace the use of fossil, so crude oil, going into those plastic products of the future? Can we substitute the crude oil with the products that you're producing?
Yes, absolutely. And that's one of the huge focuses and benefits to technologies such as ours, is that by creating or we're taking plastics which is made from oils, and we're breaking these plastics back into the building blocks, effectively breaking them back into the oils in which they came from. So these oils are now suitable as a feedstock to replace the fossil equivalents. And as mentioned, this allows us to then reduce the dependency on fossil feedstocks. And because there's no limit to the number of times we can do this, this can help create a real truly circular economy for plastics.
And just finally, and obviously it's very clear that COVID-19 is causing a range of major problems for all sectors and society on a global scale. And obviously that's having some impact on the use of single-use plastic. I was wondering, from Mura's perspective, what's the challenge that you think CatHTR can help with in terms of dealing with the sudden growth of PPE and packaging that's now evident in our lives?
I think that's right, Jeff. I think COVID has highlighted the use of plastics and our need for plastics, both from hospital applications, sterile applications, and PPE. It's highlighted our dependency on this material because it is absolutely ideal for the purposes that we need. But what the problem is not the material itself, it's how we deal with it after we've used it. And we've all seen some of the images of PPE being washed up and face masks being washed up on beaches. And this drives the need for technologies such as ours, which can take this material and recycle it. So this highlights, the COVID itself has highlighted our reliance on plastics, but also highlighted the need for technologies such as the CatHTR, which can recycle this material and reuse it.
Thanks very much. And I'm sure the growth of plastic pollution on a global scale, we run the risk of it being set back. So there's definitely a need for this sort of technology to come forward to try and address that particular problem. Thank you very much, Richard, for taking us through the technology. And I hope that everybody that's watched the webinar has found this informative. Please do get in touch using the booth that we have at the iGEM conference. So it's the Mura Technologies, part of the British Malaysian High Commission booth. So please do come in through the chat process through that. Or alternatively, come directly to us, either straight to the website, which is muratechnology.com, or just email us at inquiries@muratechnology.com. And we'll be really pleased to pick up and discuss with you your particular needs and how we can bring the CatHTR technology to your country and working with you. So once again, thank you, Richard, for taking us through, and goodbye.
Thanks, Jeff. Goodbye, everyone. Cheers.